Hello everybody, and welcome to today's video in which we will be tackling another problem from classical electrodynamics, chapter 10. This is question 2, and yeah, we'll get straight in. This is a follow on from the previous video in which we did question 1, shocker I know, which took quite some time, so hopefully this one will also take quite some time and have a satisfying ending. Anyway, the question asks, a comparatively stable self-pinch column of plasma can be produced by trapping an axial magnetic induction inside of the plasma before the pinch begins. Suppose that the plasma column initially fills a conducting tube of radius r0 and that the uniform axial magnetic induction, let's say BZ, I can't read it from this far away. It's because my thing's like, yeah. Anyway, that is the axial magnetic induction. I think I wrote B0 or just B. I was doing the problem. Is present in the tube. Then a voltage is applied along the tube so the axial currents flow and the azimuthal magnetic induction is built up. And part A asks us to show that if quasi-equilibrium conditions apply, probably quasi. The pressure balance can be written as so. Now, this is kind of, I think it's fairly, not self-explanatory, but you can see how we're ending up at this pressure balance relation fairly immediately. We'll start with the MHD momentum equation that's in the book for fluids in equilibrium. So del P is equal to 1 over C J cross B, and those are vector fields. And we'll use Gaussian units, so the quasi-static, because everything's in quasi-equilibrium here, the quasi-static Ampere's law is 1 over Cj equal to 1 over 4 pi del B, divergence of B, the curl of B rather, and substituting this back into our force balance equation, we get that del P is equal to 1 over 4 pi, why is my handwriting wobbly, 1 over 4 pi del cross B cross B. Well, that looks like an identity. So that's 1 over 4 pi B dot del. It's going to get really annoying after a while. Self-inflicted pain. B squared. And so we've just expanded and then rearranging now. We can pull things out. I'm going to take this around to the other side for 8. So del P plus B squared over 8 pi is 1 over 4 pi B dot, that's not divergence of B, B dot del B, factor out the del P plus B squared over pi is 1 over 4 pi B dot del B. Now we assume the cylindrically symmetric plasma column as given in the question. So in cylindrical coordinates, the field only depends on r, cylindrical coordinates being r, phi, and z. So we can write the magnetic fields, or rather we can say that del phi is equal to del z are both equal to 0. So we can write B as the phi direction r times the normal plus the z direction r times the normal. Let's start off with the right hand side up here. So B dot del B is equal to B phi. I'm not going to bother writing the R over R d phi plus B Z Z, and then of course our B fields. That's not a good hat. There we go. I know you expanded that. We can so phi hat changes with respect to phi. So the derivative of phi hat with respect to phi is minus r hat. So we do have a non-zero radial component. So this should be b phi over r b phi del phi hat del phi b squared phi over r hat from up yeah, those you cancel. So now we do the same thing on the left hand side. ddr of p plus bz squared plus b phi squared over 8 pi from, that seems right, b squared, yep. I've got the hat, the arrow even. I knew that would happen eventually. That was just minus b phi squared over 4 pi r because I did dr, so that from our identities above, same kind of thing going. So now the question asks us to find the global balance, so we can integrate our differential equation, which is the sum of these two terms, and hopefully it should become fairly clear what we're up to now. So integral from r1 to r2 of the derivative p plus b 8 pi dr plus the integral from r1 to 2 of that b squared over 4 pi r is equal to 0. Dr, sorry. We got the dr. Crucial. Integrating these. Actually, we don't even need to, because, well, then that becomes trivial. That's just what's written in the question. So phi squared over 8 pi between r1 and r2 plus 1 over 4 pi times the integral from r1 to r2 b squared phi, I forgot the phi there, over r dr is equal to 0. And so we have solved part A. That wasn't so bad. Touch wood. Moving on to a lot of the questions tend to be like this. It's sort of like, oh, you have an initial state which is in equilibrium, and then you have to calculate a dynamical state. I hate that kind of thing. It is fairly formulaic after a while. I noticed that with other parts of the book. I am using the first edition. I think that should be said, because I can't really find answers for any of my stuff, so I'm kind of hoping that it's right. I mean, that one's kind of obvious because it's definitely correct, but if I've made a mistake, please let me know. I don't exactly have a teacher to tell me that it's wrong, and I can't find any of the first edition answers online because the second edition came out fairly soon after. I mean, it's been very good to me, this book. so far, touch wood. I've looked ahead and it gets worse. And I'm going through it fairly slowly. Anyway, question B. Question B asks, if the plasma has a sharp boundary and such a large conductivity that currents flow only in a thin layer on the surface, show that for a quasi-static situation, the radius r of t of the plasma column is given by the following equation, with some boundary condition T0 and E0. F of t is applied to the field. There's a lot of boundary conditions here. I didn't really put A for this. I thought it was kind of always A. That's okay. So it has a sharp boundary at R equals sharp at R equals R of t. And the conductivity is approaching infinity because it's high. So currents are entirely confined to this sort of thin surface layer, because the flux inside of the plasma is like frozen. Anyway, we'll look at boundary conditions inside and outside the plasma. So inside, so for R is less than R. Something flying around my room, I think. I don't know what that is. Oh, goodness only knows. So P0 is roughly equal to 0. So we can assume a cold plasma where the kinetic pressure is sort of negligible. The total axial magnitude phi of z is pi r0 squared bz0, as I couldn't read earlier, is trapped. So the internal axial field will scale with bz of r is equal to bz0 r0 over r squared, and also b phi is equal to 0 because there's no axial current. And then for r is between big R and big R0, R is less than R is less than R0, aka for outside the plasma, it's a vacuum, so P is equal to 0. All initial axial flux is kind of gone, so BZ, because of the high conducting plasma, by Ampere's law, which we looked at before, the azimuthal field is B phi R 2I over CR, and at the boundary B phi of big R is 2I over C big R. Cool. First thing we can do is apply the result from part B. So P out plus BZ out squared minus B phi out squared. I'm not bother with commas all the time, it's a bit messy. Pi minus P in plus BZ in plus B phi squared in over 8 pi equal to 0. And we know some things here will be 0, that's 0, that's 0, that's 0, that's B phi r all squared, and that's BZ r all squared, and that's 0. So B phi r squared over 8 pi minus BZ over r squared. And we can equate the fields at the boundary here. B phi of big R is equal to BZ of big R. So 2I over CR is Z naught R naught over R should be squared. 2I over C then cancel. R naught squared over R. Great. He says, vaguely remembering what to do next. Okay, that's good. I think we can use Faraday's law. Right, so if we consider a rectangular loop in the RZ plane, which will extend radially from 0 to R0, and actually with like L, we can say the following. That will be my outer boundary times L minus E Z of 0 L, which is just E naught F T L minus 0. That's good because you just double check that is. Yeah, okay, good. That is the applied electric field. The azimuthal magnetic flux through the loop we can find by integrating B phi of R. So this in the loop is L times this from R to R0. From our, that should be from, that should be from that. One note's not happy. B phi R dr, which is L times the integral from R to R naught of 2I over CR, which is just L of 2I over C, then R, no, oh, right, let me put that in brackets as well. And we have an expression for 2I over C from up here, so bringing that down, this is equal to L B Z naught. I put a dot in there, but yeah, short times R naught squared over R. Then we should be fairly close. We've just got to deal with the other side now. Now, remembering that Faraday's law is Faraday's law. E dl is equal to 1 over C d that. The flux over change of flux of time. We know that that is equal to EFTL. Equal to E naught, sorry, FTL, and then E naught FTL is 1 over C times the derivative of that thing. R naught squared over R, then R naught over R. I think we are nearing the end. Bye bye L, because that's constant. Integrate both sides. And move the C over there. So BZ naught r squared over r, then naught over r is equal to the integral from 0 to t of c times e naught f t prime dt prime, just keeping it general, and then we can throw all our constants onto one side, and hopefully that will be t naught. So r naught over r, then r naught over r should be equal to, there's a c that goes, e naught goes, and the other r, so z naught r, the other r naught, I meant r naught, which is just t0 times the 0 to t of f of t prime dt prime equal to 1 over, sorry, that's 1 over t naught f of t prime. Nice. So we have shown that bit. Now the third bit is, oh sorry, am I being too loud? It didn't like that, did it? No. The third bit is certainly a bit. If the initial axial field is 100 Gauss and the applied electric field has an initial value of 1 volt per centimeter, oh god, the units. I remember this. 1 volt per centimeter falls almost linearly to 0 in 1 millisecond. Determine the final radius of if the initial radius is 50 centimeters. These conditions are the same order of magnitude of British toroidal apparatus, but external inductive effects limit the pinching effect less than the value here. Yes, this is the, oh my goodness, physics is finally useful case, says the aspiring engineer. Let's get on, shall we? This isn't a particularly long problem, I don't think. So we'll look at the initial parameters. See, so the axial field, B0, that's not a B. Good try again. PZ0 is 100. I'm just gonna write G for Gauss. Can I do that? No. That's probably right. Jesus, what is that flying around my light? I don't know, it looks like dust, but then it keeps making a shadow. It's very small. Oh no, we have to use stat volts. I don't like those. E0 is 1 volts per centimeter, which is 1 over 300 SV. Oh, I can't remember. Let's search it up. Yeah, that is right. Probably should have noted that down. That'd have been useful. The radius R0. See, my notes are kind of just a jumbled list of directions, like do this, do this, do this, do this, do this. You should end up, and then there's a few signposts that's like, oh yeah, you will end up with this at some point and that at some point, and that's how I kind of know I'm going in the right direction. But you know, they're not world class. We do have an initial radius R0 of 50 centimeters, and the speed of light is, we know what that is, 3 times 10 to the 10 centimeters per second. Now, the first thing we need to do is actually come up with a calculation for T0. So T0 is B Z0 R0 over CEO. It's like the bread is greater than key meme. Anyway, This is 100 times 50, yeah, over 3 times 10 to the 10 times 1 over 300, which is 5,000 over, testing me there, 8, 10 to the 8, 5 times 10 to the minus 5 seconds. Is it worrying that the thing that was testing me was this and not that? I don't know. Now, I guess the electric field just falls linearly to 0 in about 1 millisecond. TF is 1 minus 10 to minus 3 seconds. So it would just be the integral of that, of f of t in that time, sorry. Which is just half times base times height, because it's a triangle. Half pH. Just half times 10 to the minus 3 times 1, which is 5 times 10 to the minus 4 seconds. So R0 over R ln R0 over R is 5 times 10 to the minus 4 over 5 times 10 to the minus 5. Boom, 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 which is 10. Now we need to solve let x equal to R0 over R. So I think I just used a linear numerical approximation of this. It's a 10 because that's a bit of a pain to solve. I'm not going to bother, so put it in your calculator. You have a computer in front of you, just get it to do it. X is about 5.74 here. So R is just going to be R0 over 5.74, which is 50 over 5.74, which is 8.71 centimeters. I did use an unrounded value for that. Sorry, I should make that clear. 8.71 centimeters is our final pinched radius. Well, that doesn't make for a very good thumbnail, does it? When I've got all of this stuff to show off, and then, you know. Oh, I think this is the first video I've made where I've ever come out with a measured or a predicted value for something that's real. Be it disastrously inaccurate. Considering why would the field be exactly 100 Gauss or exactly 50 centimeters, and oh my goodness, the speed of light is not 3 times 10 to the 10 centimeters per second, but it doesn't matter. Anyway, I quite enjoy doing these problems. It makes a change from the derivations, as I said last week, and yeah, I hope you enjoyed as much as I did, and I'll see you next time. Thank you very much. Goodbye.